This is the first of the seminars I did specifically for New Zealand upon request. And the request was to look at wind analysis to NZS 1170 Part 2. I've come across a number of calculations and a number of designers doing different designs and coming up with different solutions based upon this wind code. And first did this a couple of years ago, and I've had to redo it because the 2011 edition has now been replaced with the 2021 edition. So throughout this presentation, I will be highlighting the differences between the old and the new version. Now, the 2021 edition hasn't actually been incorporated into the New Zealand Building Design Standard or the Building Code as yet, but is expected to do so sometime this year or perhaps next year. Now, some serious damage can be done by wind, and here are two examples, as we recalled in seminar number 3, learning from failure. And this was rather misunderstanding how wind load applies and what happens to wind when you pass it around unusual structures. This seminar is not going to be about the extreme weather, nor it's going to be around unusual structures like bridges or cooling towers. We're looking mainly at buildings because that's what the code is aimed at, and that's what we tend to do at Redco. And the question I'm often asked is, why is it so hard? Well, the behavior of wind and the forces it generates are extremely complicated, and it's not easy to put that in a simplified design guide. So we need to estimate the wind load on the buildings and therefore the wind pressures that we need to take. It's dependent largely on the surroundings and where the building is and the direction of the wind. The geometry of the building comes into it, and we're looking at usually low-rise buildings, usually rectangular, which simplifies it enormously. So step by step, the process. Where is the building? That's probably the most important factor to know, because that will determine what your regional and site wind speeds are. There are changes in the 2021 edition to the wind zones, and even the zones have been given different names in the 2021 edition. It's now the design working life, which is typically 50 years. For our buildings, we're normally looking at an importance level of 2 for ordinary buildings. And from that, we derive our annual probability of exceedance for the loads. From that, you can get your regional wind speed, VR, and your your wind direction multiplier, MD, which applies in 8 cardinal directions. We need to know what our MZCAT is, which is related to the terrain, and we also have shielding, which depends upon the buildings around your buildings. So there's topographical multiplier and there's a Lee multiplier, and you take each of those in turn. Bear in mind that some of the calculations are based on the average height of the roof, and others are based on the reference height of the roof or the piece of cladding or structure that you're looking at. So this applies in particular to tall buildings. As you go up a tall building, the wind speed will increase. For most of our projects, it's usually safe to assume a constant wind speed up a low-rise building. So find your design wind speed. You first pick your site wind speed, and you need to know it in 8 cardinal wind directions. You then multiply your regional wind speed by your various factors, MD, MZCAT, MS, and T, as we discussed before. And your design wind speed is then the maximum cardinal wind speed factor within a 90-degree sector. So here, for example, we're looking at a rectangular building. You're looking at the wind perpendicular to one of the surfaces. So in a 90-degree spread, you're looking at V site at 45 degrees northeast and V site at 90 degrees, that's the east. So you take the worst case of that or that, and that becomes your VDES. Now, for the 2021 edition, they've added another factor, the MC, and this is for climate change. At the moment, for New Zealand, the MC is set to 1. The code predominantly is looking at non-sensitive structures. So CDIN is normally set to 1. There is an equation and some factors within the appendix of 1170 part 2 to show how you derive the CDIN factor. And if your CDIN is greater than 1, then your structure is probably dynamically wind sensitive. Now, we're not normally dealing with dynamically wind sensitive structures, but they can be. So towers and tall, slender structures can be dynamically wind sensitive. The wind can excite your structure. This code is not really aimed at those kind of structures. To get your dynamic wind pressure, you take your wind speed and then multiply by its mass, and the CFig and the CDIN. So we've already set our CDIN to 1. CFig is related to our coefficients for internal and external pressure. So as you'll notice there's a little bit of Newton's laws in there, the half mv squared, looking at energy. And we take the mass of the air as 1.2 kilograms per cubic meter. Now, the internal CFig can be multiplied by an internal combination factor, and the external can be multiplied by a combination factor plus an area factor plus a local factor plus a porosity factor. Complicated, eh? Well, for 2021, they've added something else as well. And they've changed CFig to C-shape. And they've added for internals a KV, which is related to the volume and the open area, as it were, to give you a multiplier. So you can read the tables 5.1 to get your CPI, and tables 5.2 and 5.3 to get your CPE. So to give you a rough idea of where they're going to apply, you look at these various surfaces: windward, leeward, side, wind, up, down, and gable. So these are code named as W and L and S, and are for your roof. So it's the wind over your building can be quite complicated, and I suggest it's useful to have this diagram open. This is the diagram from the wind code. Even if possibly copy that into your calculations if you're looking at all the wind surfaces. Other factors, well, Ka comes into it when you've got large areas to be supported. Conservatively, you can take it as 1. There's a combination factor, Kc, which applies internally and externally. Conservatively, you can take it as 1, but if you've got 2 surfaces acting, you can use it as 0.9 or 0.8 if 3 surfaces are acting. For your internal surface, it only counts if the CPI is 0.2. That's changed for 2021. CPI has got to be bigger than 0.4. So this combination factor really only comes into it when you're looking at dominant openings. KL, right, there's a lot to talk about local area and local pressure factors, which you can get for table 5.6. So there's a permeability factor. How porous is your cladding? So internal pressure coefficients depend upon the porosity or permeability of your cladding around the building. Now, for most of us, we'll be looking at a constant permeability. So all walls are permeable. So you'll have 2 values here, the -0.3 or the 0. Where you have 2 values in your table here, you have 2 load cases, and you take the worst case that applies. Looking at internal pressures and CPI, if you have a large opening, then there's a convention we call dominant openings can come into effect. and you add up the ratios of the openings and sum them up and get a figure that you can use in this table to derive your CPI factor. And the CPI factor will vary depending upon which direction the wind is blowing. This is the new version for 2021. That's slightly different, but very similar, but they've introduced the KV factor as well. So what do we mean by permeable or impermeable surfaces in our walls? Well, if it's impermeable, all surface openings are less than 0.5% of each surface. So the openings are usually going to be doors and windows. So if you're mainly wall and only a little bit of doors and windows, then you're looking at the impermeable. But we like to put windows and doors in our buildings, and so you'll probably find that most of your walls are permeable, and that means more than 0.5%. However, that has changed. It's now going to be less than 0.1% for 2021 version. And for permeable, you've got to be between 0.1, greater than 0.1, or less than 0.5%. If you're above the 0.5%, you're probably looking at a dominant opening as well. So what we used to call dominant openings are more significant in the new version, the 2021 version of the code. Except they don't call them dominant openings, they now call them openings, just openings. So keeping with the old lexicon, the dominant opening is effectively an opening that most influences the pressure inside the structure. Pressure of the dominant opening is assumed to transfer inside the structure as it modifies the release of pressures in there. So Table 5.1a compares openings to a total wall area. So to do a little calculation here, this is how it works out. Wind pressure internal and external. So usually if you've got positive wind pressure on one face, you'll probably have negative wind pressure on the leeward face. Generally, you will probably have positive internal pressure. So pushing up on the roof and pushing on the leeward wall. But more often than not, you'll look at negative pressure as well. And what we tend to do, if we're looking at one wall, we'll take the worst case. So we'll look at that on this side, positive pressure on the inside, negative pressure on the positive pressure on the outside, negative pressure on the inside. On the leeward wall, you're looking at negative pressure on the outside and positive pressure on the inside. So you're getting the maximum. You've got to be careful when you're doing this not to create load cases that can't possibly exist, having both positive and negative pressure in at the same time. There is an issue on internal pressure. Generally, we'll take the internal pressure as constant throughout the building. This may not be the case if you've got large buildings with sealed internal walls, and they basically need to be airtight or as near to airtight as possible. So they're going to be solid walls, full height within your building, where you can have a difference in the pressure on one side or the other. So table 5.2 gives you your CPE for windward walls. Don't forget that this pressure can also apply to the underside of eaves, or if you've got an elevated structure, this can also apply to the underside of your building if it's on stilts and it's open underneath. Thankfully, this hasn't changed for the 2021 edition. Here's table 5.2b, leeward walls. So you look at the wind direction, generally looking at 0. And depending on the roof pitch, you get your external pressure coefficient. So the D and B values in here you can be careful with, because the meaning of these changes depending on which direction the wind is applied. So D is the depth of the building in the direction of the wind that's being applied. And for the 2021 edition, it's not changed. It is 5.2C. And you'll see there are a number of zones. I've added the A, B, C, D. And how far you are away from the windward edge, the pressure coefficient diminishes. So usually we look at 0.1H. So this is going to be the maximum wind zone on the side. Whereas if you're beyond 3 times the height of the building, you're down to a 0.2. Bear in mind, these are external pressure coefficients. These are not local pressure coefficients, local factors. It's unchanged for 2021. Then you look at the roof. Similarly, we have a number of zones. I've called them A, B, C, D, and E. There are 5 zones. And you measure it from the windward edge up along the roof. And depending on how big your building is, you can have up to 5. If you've got a small building, of course, you won't have that many wind zones. And you will have, in this case, you've got 2 different wind load cases in that same zone, and you take the worst case of each. And again, your D is in the depth, the direction of the wind. Unchanged for 2021. You've got a difference between roofs which are bigger than 10 degrees pitch and lower than 10 degrees pitch. So you look at table 5.3b, pick out the roof pitch, and then pick out the values depending on that given in the table. So steeper roofs have a single pair of coefficients, so you only have 2 load cases, whereas shallow roofs don't. Again, it's unchanged for 2021. If you're bigger than 10 degrees, you're looking at table 5.3c. So your crosswind or your downward slope is bigger than 10 degrees. Here are your coefficients of pressure on the roof. Again, unchanged for 2021. So here's a comparison of what's actually going on with the wind and what we think is going on, and what the code tells you. So the wind doesn't change in steps. It changes in a non-linear state. But we simplify it and split it into zones. Similarly, on the wall, it doesn't apply uniformly, but we pretend that it does. So if you look at a 3D model of that, you will have discrete pressure wind zones over your building. So your maximum wind zone, your maximum pressure, is closest to the direction of the wind. As you move further away from the direction of the wind down the building, then the wind pressure coefficient diminishes. And this reflects the experimental data as well. So how many load cases? Well, we've already seen there are 4 wind directions, 4 sides, 2 pressure coefficients per side, and you've got to take the worst case for all 4 wind directions. So there are 8 values of PI and 16 values of PE, 8 for walls and 8 for roofs. That's a lot of wind code, a lot of wind pressures. Potentially you could have up to 16 wind load cases if you really want to. If you're doing it by hand, you want to simplify it, just take the worst case. If you've got software, it will allow you to do it in all sorts of directions as well. And we can look at software a bit later as well. So coming on to local wind pressures, yeah, you have small areas. When you're looking at small areas, the wind can be quite high. And if you look at table 5.6 of the code, KL can be up to 3. It can vary from 1.5 all the way up to 3. Only one of them, the WA1, is looking at positive pressure All the rest is looking at negative pressures as well. There's a slight difference in the 2021 edition. What they've done is sneaked in this RC2, which basically says this extra local wind pressure up to 3 doesn't just apply for low pitch roofs, it applies for higher pitch roofs as well. And here is a diagram from the 2011 version. Remember that the local wind pressures only apply to your cladding and to members that are directly supporting the cladding. So that will be your purlins, your girts, your side rails, and so on. Doesn't generally apply to your main structure. Here is a 21 edition, and spot the difference. Well, here it is, just the RC1. I've never particularly liked this diagram. It's confusing as. So here's one I prepared earlier. So this is looking at the roof. So your local wind pressures usually affect the roof more than anything else, particularly the negative. So if you're looking at roof pitches below 10 degrees, you've got these very high concentrations in the corners, and then a little bit more around the eaves and the gable ends. Okay. Look at pitches above 10 degrees. You've still got that very high wind zones in the corners, but you've now added high wind zones at the apex. Now, one way around this when you design a building, if it's a steel frame building, you can reduce the spacing between your purlins, which spreads the load a bit better rather than changing the size of the purlins as you go. So up to now, we've just been looking at wind pressures that have been applied perpendicular to the surface of the structure. Now we're looking at frictional drag, and this applies in the along the surface of the structure. This really only comes into effect when you're looking at very big buildings. If you look at the factors there are tiny in there. But if you have something like multi-frame, it should automatically generate the frictional drag forces, which can add a little bit on to the loading, particularly out of plane for your larger buildings. And it's unchanged for 2021. So summing it up, wind speed. Take your regional wind speed, you look at direction and topographical factors and your building orientation. So there you get V site comes from VR times MD, MZCat, MS and MT. Get your internal pressures, which are dependent on your permeability and your openings ratio. You multiply the mass of your air, your density of the air, by your wind speed squared, with all the multipliers added onto that. External pressures, similarly, 3 wall faces to look up, 3 roof slopes to look up, and you then multiply that by all your factors and your design wind speed to get your pressure on the external face of your cladding. Now don't forget, obviously, your external pressure acts at the same time as your internal pressure. So your structure has to support both of these things. Define wind loads, combine the wind directions, the factors, and then you can get what I call WU1, 2, and so on. So wind loads ultimate in across or along. So we're usually dealing with rectangular buildings. So we'll have a wind load across the building and a wind load along the building. You'll have that at ultimate limit state, but you'll also have that at serviceability limit state. So you're designing for strength, but you also check for the serviceability, usually deflection. For lightweight buildings, actually, our lightweight portal frames, the deflection under wind load can be the critical factor. So the structure could take lots and lots of load above the design load, but the deflection is too much. So for the 2021 edition, we put in the new figures, including our climate change factor. We've swapped our C fig for C shape, and it all spins out with pressures on the internal and external faces. Canopies. Yes, don't we just love canopies? Canopies, and we've then got to carports. So the wind around canopies will vary and be different from your main building. Now be careful that your canopy is a canopy and not just an extension of your roof. If it's merely a roof overhang, and then you take the wind loading from your roof overhang and allow for the external wind pressure underneath as well. And this only applies to certain roofs. So check that the limitations of the code actually apply to these figures. So we've got a whole series of tables in the appendix, Appendix D, depending on the type you're looking at. So you're looking at either monoslopes, pitched, troughed, high par-free roofs, which is a bit unusual, canopies, and partially enclosed carports. The 2021 edition is now in Appendix B, but it's very similar. I think all the figures are the same. So for a pitched free roof, you're given net pressure coefficients. So you don't work out actually internal pressures versus external pressures. You're just given an overall net pressure. And depending on whether you're blocked under, so what's happening to the wind underneath your roof? If there's a wall here, or this basically storage, you've got to consider it to be blocked. And again, read the fine detail of the code and it'll tell you how much you consider to be blocked as well, because you can see the values for blocked under considerably higher than for empty under. If you think about it, it makes sense. If you've got a freestanding roof open at both ends, the wind will just wheel through it. But if you put lots and lots of storage material in here, then the wind stops and then goes up to your roof as well. The other way, of course, it'll be blocked by the house. The 2021 edition is very, very similar. It's just now in figure B4. Open canopies and awnings, very similar. They're attached. The idea of these, they're attached to a building. And again, remember, are you checking a canopy or is it just a roof overhang? If it's just a roof overhang, then treat it as a roof, not a separate canopy. And it can get very complicated down here depending on the dimensions. So there's another height you need to think about. That's the height of the canopy. So here's the 2021 edition. Very, very similar to the previous edition, but we're just now calling it Appendix B7. So enclosed carports, very common in New Zealand. And if you think about it, the wind, when it hits, particularly in this direction, is going to be trapped in here. So if you've got a roof over that, the wind in there is going to raise the roof. And so depending on which direction you're looking at, the values can be quite high. The 2021 edition is pretty much the same, it's just got a new figure number. So just for a bit of fun, we'll compare wind speeds, and the famous wind speed chart is called the Beaufort scale, well over 100 years old, probably 200 years old now. And they had a scale of 1 to 12 from light air through to hurricane. And you can look at the NZ 3604 figures and think, well, a low wind speed is even higher than a storm. But the Beaufort scale is a 10-minute average. The wind speeds you're using in 3604 are taken from 1170, and that uses a 0.2 second peak. So you're looking at a difference between a peak and a mean, and the peak is going to be considerably higher than that. And we will talk about 3604. So 3604 is the timber code for buildings that don't need an engineer, non-specific engineered design. So this allows architects and buildings to think they can design a house. And it is aimed at lightweight, low-rise timber frame buildings. And they simplified the wind zones into low, medium, high, very high and extra high. And if you're outside of those wind speeds, they should be coming to you as an engineer. So SED, specific engineered design, in there. So what are the issues? Right, so Redco has a number of spreadsheets, and the spreadsheets will pull out the wind load for you. And again, the spreadsheets are simplified versions of the wind code, and they will do you a long and a cross, which for most of our simple buildings is usually good enough. Dominant openings. There are mixed feelings about dominant openings in Redco. I think you should think about them and incorporate them in your design. For most houses and house-like buildings, they're not an issue. But for warehouses, which have large doors, and large doors tend to be left open, or if the doors are likely to be left open, you have a dominant opening. But definitely the permeability of one side is usually considerably higher than it is on the other side. Don't forget the doors and windows. If you are saying that you don't have dominant openings, then your doors and windows have to be designed to withstand the wind pressures, the design wind pressures on them. And we put this little caveat in our design features report that doors and windows need to be designed to withstand these loads, and that's usually a separate person's job. Think about where the wind goes. So if your door or window takes the load, where does the load go? Well, it's got to get to a door header or window header, down to the mullions, or maybe even to the main frame, but it's got to go somewhere, and you need to chase that load down. And don't forget that lintels and purlins can be subject to biaxial load. So a pitched roof, your wind load applies perpendicular to the roof surface, whereas the gravity loads and the live loads apply vertically downwards. So most lintels and purlins will be subjected to biaxial load. Now, if the roof pitch is shallow, it doesn't matter. It makes very little difference. However, when your roof pitch is more than about 20-25 degrees, it might be worth considering if you're pushing the boundaries of your purlin design. We have a handbook for wind loading, and it's come from the Australian Wind Engineering Society. This is available through the standards directories on the Common Drive, and so you can read to your heart's content this particular document, and it tells you all the background behind the code, the history and the changes of the code, so forth. NZBC, right. 1170 Part 2 may be adopted by the New Zealand Building Code around the end of this year. And that's the same note I put last year, sorry. So hopefully it might be incorporated at the end of this year, maybe next year. And because of that, the brands map is out of date. There is a brands map available online. It's a very useful tool. It's got all sorts of useful information on it, but it is a simplified tool, where that's why architects love it. And similarly, NZ3604 is a simplified design code, and they simplified the wind zones down to this low, medium, high, extra high. And they're not applicable to structures outside the limitations of NZ3604. So bear in mind, NZ3604 is aimed at lightweight timber-framed house-type structures. So there's a limit on the house size, there's a limit on the number of stories, there's a limit on the overall floor plans, and so on. But it allows architects and builders to design houses, basically. Councils like it because they can understand it and they like it, and they'll keep referring to it. There is a Mathcad example I developed, which is based on this code. So here is the Mathcad version, and you just take all the equations out of the code and put them into Mathcad. So you put these as an input, the MDs and so on, terrain categories, the MZ cats you can work out, and just multiply it all together. That gives you your design wind speed. There is actually a clause that says your minimum design wind speed is going to be 30 meters per second. It's not usually the case that that dominates either. To derive your pressure coefficient, you add on your combination factors, your area factors, your local pressure factors, and so on. And you derive your external pressure coefficients from tables 5.2 onwards, for windward, leeward side, and so on. And that will allow you to determine the C-fig for each of these surfaces. That will give you your net pressure for each of these surfaces. So your wind, leeward, side, wind, and so on, upwind. And again, to remind you of where all of these things apply, pick out the diagram. And you can eventually derive your serviceability wind codes, usually by picking out the factors as well. Local wind pressures. You can look at combination factors. You can look at the KL factors in various areas. So 1, 2, 3, 1.5, and so on. That will give you your maximum wind pressures on local areas and remind you where they apply and so on. I did do a 2021 edition. The main difference is the regional wind zone has changed its name. The combination factors can be changed. There's this new KV factor. It's a bit complicated to work out, but you can derive it as an equation like that, depending on how big your building is. So the influence of your dominant openings is dependent on the internal volume of your building as well. And we do the same thing again, derive the ultimate wind pressures. Each of the surfaces, windward, leeward, sides, and so on. And look at serviceability wind states and our local wind pressures. Let's see where they apply. Okay. So that's the end of seminar 6. Looking forward in 2 weeks' time for our next seminar. And we're looking at seismic assessment of existing buildings. We're looking at the technical guidelines for engineering assessments from the New Zealand Society for Earthquake Engineering. It's primarily aimed as an overview. So this is the kind of information you can tell your clients.